Hello, everyone, and thanks for sort of showing up to this emergency Stat 4243 lecture. I appreciate everyone's sort of understanding as I try to sort of get healthy again. And, I hope that this format works for us to cover the content that we are hoping to cover. Of course, if you have any questions about anything that I talk about in this video, please feel free to send me an email, set up some time. We can talk over Teams or we can talk in person sort of once I'm back. And can address sort of any of the concerns that you might have there. In today's lecture, I'm going to try to just pick up where we left off, finish talking through some of the concepts that we've been looking at, right? And then sort of introduce some of the ideas that we're going to continue to explore from this point forward. Right. And so just like as a brief reminder, we've been talking about Monte Carlo integration, right? And the idea with Monte Carlo integration is that we're going to be able to use random number generation to take integrals, right? And we've seen sort of a whole bunch of techniques for doing this, and in particular for trying to reduce the variance of our Monte Carlo integrals, right? And so we've been talking about sort of all of these ways that even without needing to increase the sample size of our simulations too much, that we're able to sort of achieve better results than we otherwise would. And so with today's lecture, we're going to start by talking about sort of the last variance reduction technique, right? So we saw antithetic variables, we saw control variates. In last class, we were looking at importance sampling, right? Where we're trying to match the density to the function we're trying to integrate. And in today's lecture, we're going to look at something known as stratified sampling. So if you've actually taken any sampling theory before, then stratified sampling should be sort of familiar to you. And the idea is going to be quite similar in terms of what we're doing with the Monte Carlo integrals, right? But it's going to essentially be a way of us reducing the variability of the integral that we want to take, right? And so can open this up here and start to sort of talk about what it is that we're thinking through when we're thinking about stratified sampling, right? And so as always, if we think about sort of what we're trying to do here as solve some integral from a to b of gx dx, right? And we'll assume that this is sort of well-defined. Then what we might be able to do, or what we might think to do, is to, instead of integrating over the range a to b directly, maybe what we do is we generate a whole bunch of cut points, right? And so if we have sort of this interval that we're on here, a to b, then maybe what we do is we call a p1, and then we draw in a p2, and then a p3, and then, so forth up to, I don't know, for instance, say pk, and then pk plus 1, right? And so here we formed sort of k distinct sections, right? And we're just dividing up this integral. And if we do this, then what we can say is that this integral is going to be the integral from p1 to p2 of gx dx plus the integral from p2 to p3 of gx dx, and so forth up until the integral from pk to pk plus 1 gx dx. Right, and so why might we think about doing this? Well, the basic idea that we're going to be sort of thinking about here is that if we have some function, right, we know that the sort of variance of our overall estimate, right, so the variance of theta hat, which is what we're estimating the integral with, this is going to have variance that is sort of like variance of this function divided by m, right? And so we've talked about how the variability of this function is sort of the key driving force between how well our integration technique works. And so the thing that we might think is that if we have a function where over these different intervals, the function is less variable, right? So if over this range and then this range and then this range and so forth, if there's smaller variance on each of these different intervals, then overall there's going to be a smaller variance of this function just by looking at each individual segment together, right? And so we can take sort of an extreme example of this, right? And we can write down what we might call a piecewise constant function. So what is a piecewise constant function? Well, a piecewise constant function is any function that has a constant level for a set period of time and then jumps to a different level, right? So we might have something that we're thinking of like this, and then we jump up to here, and then we jump down, then we're here, and then perhaps up there, right? And so we're going to have something like this. And the thing to note is that if we were to cut up this function over each of the cut points here, right? So draw cut points onto each of these, right? And we call this sort of P1, and this P2, and this P3, and this P4, and this P5, right? Then over each of these intervals, the variance of the function is 0, right? So this is g of x here. But on this interval, the variance of g of x is 0. And same thing with on this one, and same on this one, and so forth, right? Anywhere that it's constant, it's going to have a 0 variance. And so if we had known this, we could have divided up this function so that we integrate each of these components themselves. And then what we're going to find is that if we were to use Monte Carlo on just this first segment, or Monte Carlo on just this second segment, and then we add them all together, well, we're adding together a bunch of independent estimates, right? What happens on the first segment doesn't depend on what happens on the second segment, and so the variance is just going to be the sum, but each of these is going to have variance 0, right? And so doing this is going to end up with an estimator for here with theta hat where it's variance of 0, and then we'd have, theta hat 1, and this will be theta hat 2, and this would be theta hat 3, and so forth, right? And all of these are going to have variance 0, and because of that, we're going to be able to estimate the overall integral here with a lot lower variance than if we had just treated this as one single function throughout. Okay, and so essentially what we're thinking about with stratified sampling is that first we're going to split the interval, and we'll say into k chunks. Right. The second step is to find theta hat k, we'll call it. Right. And what this is going to be is going to be equal to, say, 1 divided by, oh, and I should use a different indicator other than k, so we'll call this theta hat L. It's going to be 1 divided by ml, where L is going to be the number of points we're sampling in each of these intervals. The sum from I equals 1 to ml of g x I, and this is for L equals 1 through till k. Right? And then essentially what we want to do is put together all of these pieces into our overall estimate, right? And so then we sort of form, say, theta hat is equal to perhaps 1 over k, sum from L equals 1 to k of theta hat L, right? And you might not want to do a simple average here if these MLs are different, right? So we can sort of talk about how we're going to actually end up dividing up all of the points across the whole situation here. But overall, what we're thinking about is we divide up the interval, we fit a Monte Carlo integral on each segment, and then we average over the whole interval itself, right? And that's sort of going to give us the overarching integration here to the point that that sort of will work out nicely for us. And so then sort of our questions become, how do we actually go about splitting the interval? How do we decide, how many points are going to be into each of them? And also with this one, do we actually just want to take a simple average, or should we do something that's perhaps a little bit more complex with it? Now, there's going to be a whole lot of different methods for doing this. And the essential idea is that you sort of want to be dividing up the interval on the basis of the function itself, right? So with this piecewise constant model that we had here, it wouldn't have really helped us that much if we had divided the intervals, like say here, but then we go like there as the next one and there, right? That might help a little bit, but it's not going to help a whole lot. And so we do want to be a little bit smart about it, but oftentimes it's going to be hard to know exactly how to do this, right? And so oftentimes we're going to rely on some heuristics in order to actually do this process in actual fact. And so to sort of start formalizing through this a little bit, what we'll do is we'll start defining out some of our notation a little bit more concretely here. So we have our k intervals, right? And what we're going to do is we're going to end up sampling a total of m points, right? Where m is going to be equal to m1 plus m2 up to mk. And each of those is going to be the number of points we're sampling within each of those intervals, right? And then what we can think about is sort of what is the probability that we actually end up sort of sampling a point from within this interval, right? And so if we think about sort of the setup where we're sampling x from some density, say f, right? Then one of the things that we might think to do is take the probability sort of proportional to how likely it would have been to observe something within that range in the first place, right? And so we can sort of think about the probability that, say, pj is less than or equal to x, which is less than or equal to pj plus 1, right? So what's the probability that we're actually sort of following into that jth interval, right? Where we remember that our p's are our cut points. And so to be less than p2 greater than p1 means you're falling in the first interval. To be bigger than p2, less than p3 means you're in the second interval, and so forth, right? And so maybe we take this and we define this probability right here to just be called pj. So it's the probability that a randomly selected x falls into any of the given intervals, right? And so then perhaps what we want to do is, instead of just equally weighting everything, we might want to weight things according to this actual probability here, right? And so what we could do then is, for instance, take mj is equal to pj times by m, right? So we're putting in the pj proportion of the points into m, and of course you're going to have to round off this value, but in so doing, you're sort of taking a proportional number of points as what sort of deserves to be in there. And then we can sort of ask ourselves, okay, so if we use this setup, right? So we're taking this number of points from each of our intervals. We've divided up these sort of cut points based on the basis of the function, and perhaps they're equally spaced. Perhaps they're sort of selected based on how we know the structure of the function looks, right? Then what we could ask is, okay, so if we actually form this out, right, then what is going to be the variance of our overall estimator, right? And this is sort of what we want to show here. And ideally, what we're going to be able to show is that the variance of this is going to be lower than the variance if we hadn't done any of this splitting, okay? So to actually work this out, sort of come over here, and let's, perhaps draw out this picture, make everything as concrete as we can, right? So we have some function g of x, right? It looks like whatever. So this is our function right here. What we've done is we've come in and we've divided the interval into k different points. And for now, we can just think about dividing this up equally. But you could think about sort of doing this sort of more selectively, right? Then if we're thinking about the density that we're actually sampling from, right, we have some x is coming from f of x, and the probability that x is in the jth interval, so pj to bj plus 1, is going to be equal to just pj here. And then what we do is we take for each j from 1 up till k, we sample mj times by, or sorry, I guess mj, which is equal to pj times by m points on the interval pj to pj plus 1, right? We calculate theta hat j is 1 over mj times the sum from I equals 1 to mj of g of x just computed on those samples there, right? And then at the end, we come together and we say 3 theta hat is then going to be equal to, and we sum over each of the j's, so j equals 1 to k, and we're going to take pj times by theta hat j, right? And so that's sort of the full process that we're thinking about here. And our question is, what is the variance of theta hat in this case? Right? And so we can write this as the variance of this summation right here, right? J equals 1 to k of pj times by theta hat j. Note that each of our estimates is going to be independent of one another because all of the points we're generating are independent, and so that's where the sort of randomness is coming there. We have non-overlapping intervals, and so we have this is going to be equal to the sum from j equals 1 to k of the variance of pj times by theta hat j, right? Pj is some constant, right? We could work out what that's going to be, and so what we're going to get is that's going to be the sum from j equals 1 to k of pj squared times by the variance of theta hat j, right? And so if we're actually thinking about what theta hat j is, right? Well, theta hat j is going to be given by sort of the standard estimator that we've been using for our Monte Carlo, except restricted to this interval right here, right? And so what we can say is that the variance of theta hat j is going to be the variance of g x on the interval j divided by the number of points that we've sampled, which is divided by mj, right? And mj we might want to write as pj times by m, right? And so if we sort of take this variance term here and we just call this, say, sigma j squared, right? So sigma j is the variance of the function on the jth interval. Then simplifying this down, we get j from 1 to k. This pj squared is going to cancel out the pj in the denominator, and so we're going to be left with pj times by sigma j squared divided by m, right? And we can pull that m out front, and this leaves us with 1 over m, the sum from j equals 1 to k of pj times by sigma j squared, right? And so that's going to be the variance of our estimator here, right? And the question for us is this smaller or larger than the variance of the overall estimator, right? If you hadn't actually done the stratification. And so what we would want to do here is think about what is the variance of the standard, right? And so maybe I will call this, what's the variance of theta tilde, where theta tilde is just going to be the estimator if you're not doing any of these stratification techniques, right? And what we know, and we've been saying this sort of the whole time, is this is 1 over m times by the variance of g of x, right? And so what we want to do here is we want to somehow frame g of x in terms of sigma j squared, right? And so what we could do is we can think about writing out the variance of g of x here using our law of total variance, right? So the variance of g of x we can write as the expected value of the conditional variance of g of x, and all I'm going to condition on right now is something that I will call h of x, right? H of x could be anything. We're going to pick out what h of x is going to be in a minute here, but for now we'll just think about h of x is something, right? And this is true for any of these h of x's. So you have to add the expected value of the conditional variance plus the variance of the conditional expectation, right? And so what I'm going to think to do is define h of x equal to j if pj less than or equal to x less than or equal to p of j plus 1. Right? So if h of x is equal to 1, it means that x is in that first interval. If h of x is equal to 2, it means that x is in the second interval. Right? And why is this useful for us? Well, if you know which interval x is in, that's how we've been sort of defining these sigma j squareds. Right, and so we could think about this first term here. The expected value of the conditional variance of g of x given h of x, right? And so for this expectation, we can sum over the different values here, right? And think about sort of for each of these possible situations, I guess, sort of put differently. I'll try to frame this more clearly, right? We know that this variance right here is going to equal sigma j squared if h of x equals j, right? And so then we need to take the expected value of this, right? And so we know that j is anywhere from 1 up till k, and so then the expected value of the variance of g of x given h of x, right? We sum over the possible values here. J is 1 up till k. The probability that hx equals j is pj by definition times by sigma j squared. All right, so the expected value right here is this term that we have, right? And so this deals with this first term. And so then what we need is this variance of this expected value term, right? And so the expected value of g of x given h of u, right? Well, what we could define is we could define some extra notation here, right? So if we define this to be, say, theta j, right, the expected value of g of x on the jth interval, so this is h of x equals j, right? Then we can take the variance of this is going to be sort of the summation here, so the variance of the expected value of g of x given h of x is, once again, we're going to sum over the possible values for h of x, right? And then for each of these, it's going to be equal to, say, pj times by theta j minus theta, which is the overall expectation, all of this squared. And the only thing that we will want to point out here is that, of course, this right here is going to be greater than or equal to 0. And the only way that that's ever going to equal 0 is if we have theta j is equal to theta for all of the different values, right? So if you have some constant function. And so we can sort of say that unless it's constant, this is just greater than 0, right? But so then what are we actually saying here? Well, the variance of g of x is equal to this term plus this term, which is greater than 0. And so taken all together then, the variance of theta tilde is 1 over m times by that first term that we were looking at, which is sum over j 1 to k, pj sigma j squared, plus something k here. K is a bad example. I will put in a different notation here. We'll just add on omega. And omega, what we can say is that omega is greater than or equal to 0, right? And so if we compare this expression to this expression, right? Well, this first term is exactly that variance that we found, and then we're adding on something greater than 0. And so in other words, variance of theta tilde is going to be greater than or equal to the variance of theta hat, and the only way that they're equal is if we actually have a constant function across the whole path there. And so what we're saying is that by doing this stratification, where we're proportionately allocating the different points to it, we're guaranteed to reduce the variance here, right? And so, again, if you're sort of struggling with any of the details there, all of the details will be in the notes, and we'll scroll through those in a moment here. But it's worth sort of just, re-emphasizing this point. Even if we're looking at a function that looks something like this, right? The idea is that as long as you have like a reasonably well-defined function, over any smaller interval, the variance is likely to be smaller than over the whole function itself, right? And so because of that, if what we do is we say, okay, well, like, let's just calculate this integral, and then let's just calculate this integral, and then let's just calculate this integral, and so forth, right? Then each of those individual integrals is going to have a smaller variance. And so when you add them all up, you're going to get an overall smaller variance as well. And so this sort of stratified technique is going to, again, be quite effective. It's going to be quite effective in any number of situations. But the nice thing that we see here is that as long as you're using this proportional allocation scheme, you can't ever do worse with it, right? So even if it doesn't work out really well for you, as long as you're not sort of putting too much burden into actually working through the details of that, then you're not ever going to end up in a worse off position, all right? And so let me just open up our notes over here. So again, in the notes, all of this argument is walked through in perhaps a little bit more detail than what we just talked about. But we talk about sort of doing this division of our interval, right? We write down the integral itself. We're using the piecewise constant model to sort of do this motivation, right? And in this example specifically here, you can see that there's zero variance on each of those flat strips, right? But we're going from roughly 0 down here up to 40 over here, right? And so there's going to be a lot of variation in this function as a whole, but there's no variation on any one of these exact flat parts, right? And so then we can work through, we define our notation about being in each of these intervals, right? And we work out what's the variance of this estimator, work out what's the variance of the underlying estimator, right? And therefore, what we know is that the variance of theta hat is going to be larger if you're using proportional allocation. Now, almost always, what we're going to do is we're going to divide up our region into equal parts, right? So we're not going to sort of be trying to cleverly split this up. We're just going to say, 0.2, 0.2, 0.2, 0.2, 0.2. In this case, that works out quite nicely, but we're just going to divide it equally. And then we're going to use sort of proportional allocation within each of those, right? So typically that's how we're going to do, but this actually still works even if you're not using proportional allocation, or even if you're not dividing the region evenly. It also turns out that instead of using proportional allocation, the actual best bet is to be proportional to not only the probability that you're in the region, but also the variance or the standard deviation within that region as well. However, we don't typically know the standard deviation, so that's not normally a very helpful addition there. And so we'll just typically take things being proportional to the probability that you fall in the region times by the sample size. So we can actually, apply this. So we have this integral here, right? We want to integrate 0 to 1, e to the negative x, 1 plus x squared dx. And we're going to use the uniform distribution on 0, 1 to do so. So in the simulation that we're setting up here, we're going to try a whole bunch of different stratification levels, right? So we're going to use just a single stratification, which is just the normal Monte Carlo integral. We're going to use 2, 4, 8, 16, up to 50 different strata. We're going to just divide up the number of replicates evenly because we're using the uniform distribution, right? And so the uniform distribution is going to equally allocate to each of them. And then what we're going to do is we're just going to run through the results of this several times, right? 200 times each. So in each of them, we loop over all of the different cuts that we're making, right? And then essentially what we're ultimately trying to do is we're generating a uniform from the minimum to the maximum on that interval, right? So then otherwise we're just taking the mean of our function applied to the uniforms, just like we would do before. And then we end up taking the mean over all of those possible values, right? So we're just sort of implementing the exact process here. And if we look at the results, well, then what we can see is that as you add more and more cuts, you get sort of reduced variance, right? Where the standard integral has quite a large variance over here. By the time that you're doing 50 cuts, we have very little. Now, this is more computationally expensive, ever so slightly, but still you get this major sort of variance reduction, and that's what we would expect to see. In certain cases, you'll get larger variance reduction than in other cases, right? And so that's sort of the utility of this stratified sampling. So with that, that sort of ends the discussion that I wanted to have about Monte Carlo integration techniques. And specifically, we saw what is sort of the underlying logic of Monte Carlo integration. We saw how can we go about improving our Monte Carlo estimators? How can we reduce the variance of the estimators here? And throughout all of this, right, one of the things that I've been sort of emphasizing is that a lot of the integrals we've been looking at in these notes here, if you're sort of reading through in some more depth after the fact, are not integrals that we actually needed Monte Carlo for. Right, and so why is Monte Carlo actually useful? And so I'll just spend a few minutes here talking about the actual utility of Monte Carlo integration, and I would encourage you to read through some of this a little bit more. But the basic premise of Monte Carlo integration is that it provides us a way of solving an integral numerically, which is independent of the dimension of the integral itself. So the thing that I sort of mean by this is that every one of the integrals we looked at has a single dimension to it, right? It's just the integral of a univariate function. But you could imagine taking, say, a double integral or a triple integral or a 10-way integral, right, over a function of 2 or 3 or 10 variables. And as you do this, in general, the integrals are going to become a whole lot more complex. But if you think about what's happening with Monte Carlo integration, the only thing that we would have to change here is we would need to be generating a multivariate distribution, generating from a multivariate distribution rather than a univariate distribution. And we would need to be evaluating a 10-dimensional function rather than a 1-dimensional function. But otherwise, we're still going to be just generating the same points, evaluating the same function, taking the average. And so because of this, the error from our integral does not depend on the dimension, right? So the absolute error of any Monte Carlo integral is going to be on the order of 1 over the square root of m, where m is the number of points that we sample. It doesn't matter whether we're dealing with a 1-dimensional case, or we're dealing with 3 to 12, or we're dealing with 500 dimensions, right? So this is a really, really powerful result from Monte Carlo. And sort of the reason for it is that almost always the other forms of integration, the other forms of numeric integration, are going to depend on the dimension, right? And so generally speaking, numerical integration techniques scale exponentially, right? And so the example I'm giving here is that if you have m equals 1,000 samples is enough in 1 dimension, then if you go to 4 dimensions, you require whatever this is, a billion, a trillion, 1,000 to the power of 4, right? Count out the zeros there for yourself, right? So as you start to increase the number of samples, or the number of dimensions, the number of samples that you need is going to blow up exponentially. However, if m equals 1,000 samples is enough for d equals 1 in the Monte Carlo case, then m equals 1,000 samples should be enough for d equals 4 in the Monte Carlo case, right? And so because of this, while Monte Carlo tends to be less efficient in a single dimensional problem, right? You can get numerical integration that goes by faster. As the number of dimensions scale up, this is sort of no longer going to be the case. Because of this, when you have really high dimensional integrals, you're going to be in a situation where Monte Carlo techniques become incredibly useful for us. So there are some finance applications, for instance, that would be taking like 300 or 400 dimensional integrals, right? And to try to do that using numerical techniques is totally infeasible, but there are ways that you can sort of get the Monte Carlo integrals controlled in that setting, right? And so that becomes the really big power of this. This is where they come up in sort of engineering, in sort of particle modeling, in finance, right? Where you have these integrals that are arising with tons and tons of factors that you need to be considering, that you need to be integrating over. Now, I will make a point that while technically the absolute error of a Monte Carlo integral does not scale with the dimension, that's not to say that in higher dimensions the problem does not get harder, right? And so the issue is that oftentimes we will end up actually still needing more samples in higher dimensions because higher dimensional problems are sort of more sparse in a way. So sort of put differently, if you have a situation whereby you don't have error that's scaling with dimension, but you have error that just starts out really high, you may still sort of need extreme numbers of samples in order to get that to a reasonable level. And so in practice, while there are many high dimensional integrals that Monte Carlo is very appropriate for, it's not always going to end up sort of solving the day, right? So we can't always sort of rely on this theoretical capacity for there to be sort of dimension independent scaling. But with that said, that sort of gives you, a very brief overview of how Monte Carlo techniques are actually going to work, right? Hopefully that makes a little bit of sense. Hopefully you sort of understand how we're going to come to terms with sort of trying to do the variance reduction and sort of why we need to be thinking about doing the variance reduction. Now, the next thing that I want to talk about in this class is something known as resampling or bootstrap or jackknife. And so I'll open up the other set of notes over here. And again, these will be posted to the course website. They are sort of a living document right now. I haven't quite gotten to the end of all of this, but we have more than enough to start our discussions here. And in sort of the last little bit of today's lecture, what I want to start talking about is the difference between what we would consider to be parametric inference in statistics and non-parametric inference in statistics. So perhaps some of you have seen this before, but in general, there's two major classes of estimation techniques for statistical estimation or for statistical inference or for hypothesis testing. And this is either through a parametric framework or from a non-parametric framework. There are also sort of methods that blend the two, known as semi-parametric methods, but for now, we'll sort of ignore the semi-parametric situation. And the basic idea is that with a parametric technique, and this will be what you're sort of used to dealing with in your statistics classes, we make some underlying assumption about the distribution that we want to deal with, right? And so if you think about something like doing a t-test, right? With the t-test, we're assuming that the sampling distribution is going to follow a t-distribution. And normally that comes from assuming that the statistic is normally distributed, right? But we're making some distributional assumption. If you think about doing maximum likelihood estimation, right? So maximum likelihood estimation is very parametric in the sense that you assume that the data are being sampled from some known density, and then you work with that density to estimate the different parameters, right? If you think about doing certain tests from your linear regression class, you would have sort of assumed that the errors were normal, and you don't need that for everything within linear regression, but you do need that for certain things in linear regression. If you think about forming a confidence interval in the small sample case around the sample mean, right? All of these things, the way that the procedure works is you assume the distribution, or you assume something about the distribution, and then from there, you use theory to work out what you should be doing. Now, parametric techniques are great because they are efficient, like in the sense that they give lower variance on the estimators. And they tend to be sort of easier to work with from a theoretical standpoint. So we can actually say very concrete things theoretically about parametric estimators. However, in the real world, we almost certainly don't know what distribution our data follow, and almost certainly they're not going to be following some nice distribution. And so this brings us to the idea of forming non-parametric techniques. And so with non-parametric techniques, The idea is that instead of us assuming that we know what distribution things are going to be coming from, we try to develop statistical techniques that will work no matter what the distribution is, or perhaps with some restrictions about what the distribution might be. And so we can start to write down what this non-parametric framework looks like. If you think about how we would normally have set up a problem in a parametric setting, right? So if we think about parametric setting, then typically what we're going to say is something like, assume that x1, x2, xn come from some known distribution, right? And probably you're going to assume their IID from this distribution. And then what we would take is, for instance, maybe theta is a parameter, and we want theta hat to estimate. Right, so this is sort of the situation that we're used to working with. In the non-parametric case, right, so if we take a non-parametric setting, then what we're thinking about here is that x1 to xn are still going to be IID from some distribution, but we typically will just call this distribution f, or maybe we'll call it p. And the idea is that there's some CDF that is going to be followed by all of these values, but we don't want to know anything about it, or we don't want to say anything about it concretely. And then when we start thinking about our parameters, right, so we'll think about getting theta still, but it's going to be theta as a functional of f, right? And so what's a functional, right? So we're calling this a functional. And a functional is going to be a function that maps from a space of functions to the real numbers, right? So the idea here is that we're going to have some space here, and we're going to keep all of our CDFs. All of the possible CDFs are going to be here, right? And these are going to map into different values for just the real numbers, right? And so we can sort of draw out our circle over here. This circle is our real numbers, right? And so the functionals are mapping from the CDFs to the real numbers. So if I give you the CDF, then you apply the functional and you get a real number out of it, right? And then we still want to come up with theta hat, right? But theta hat is going to be estimating this sort of functional, where it should work no matter what f is going to be, right? So to make matters sort of concrete here, we can consider perhaps an example. And so if we take x1 up to xn, IID from f, then we might define theta of f as the expected value of the distribution of x, right? So it's just the mean of this distribution, right? So how is this a functional here? Well, we could think about writing this as the integral over sort of the entire, say, real numbers here of x times fx dx, right? Where fx is going to be the density here. But perhaps the density doesn't exist, and perhaps this is sort of too restrictive for us. So the other way that you might see this written out is to say that this is going to be the integral over the real numbers of x, and then we write it in this notation, df of x, right? And sort of what is this getting at? Well, this is getting at the fact that if you were to take the derivative of our CDF here, right? The derivative of the CDF is going to give us our density if it actually exists, right? And so this idea is that this integral is literally the way that we define the expected value here, right? And this integral, to sort of fully parse, you would need to take some measure theory. But the way you can sort of intuitively read this is that we're taking the derivative of this function here, right? The derivative of this function is the thing that we're integrating with respect to, right? And so you can sort of think about that as doing some sort of u substitution, where if you take d by dx of f of x, right, then that gives us the density. And so then d f of x is going to be fx dx, right? And this is sort of perhaps an informal way of sort of arguing what we're talking about here. But the reason we like to write it in this format is because it makes explicit the function that we're actually sort of integrating with respect to, right? And so theta hat becomes a function of f, or a functional of f, and we have f directly right there, right? And so ultimately, this is just the expected value that we all know, right? And so one way that we might think to estimate this is using, say, x bar. And it turns out that x bar is going to converge in probability to theta of f no matter what, right? It doesn't matter what your distribution is, assuming that your expectation actually exists, well then your sample mean is always going to converge to that mean value, right? And so what we can say is that the sample mean is a nonparametric estimator, right? And the reason that we say that the sample mean is a nonparametric estimator is because we do not need to make an assumption about the distribution of the data in order for the sample mean to be valid for us. Okay. We can look at another example here, right? And so another one that hopefully is perhaps common for you in this class. And that's the idea of our regression equation, right? So if we take y is equal to, for instance, beta 0 plus beta 1x, and maybe, you know what, we'll just use the general regression equation. So beta transpose x plus epsilon, where this is an error term, right? You've probably seen this derived where you assume that the error term is normally distributed, but we don't actually need to assume that, right? And then what you can say is that if you take theta of f, right, where f is going to end up being the distribution of, say, y here, is going to be the expected value of y given x, right? And so you could write out this expectation in some sort of more explicit form, right? We could write this out as the integral of beta 0 plus beta transpose x plus epsilon of df of x, right? And so this is sort of, we have conditioned here, actually, that should be df of epsilon more correctly, right? And so we could do this, right? Another sort of more natural thing to do here would be to say, take theta of f is equal to beta 0, beta 1, right? And so this is, or not beta 1, just equal to theta, beta 0, beta, right? And so it's going to be equal to sort of the true parameter values there. And again, you can actually get this sort of by inverting this equation, or by sort of writing this down. But ultimately, we're just thinking about these two parameter values as being defined in some sense by the distribution of y, right? And if you remember your ordinary least squares estimators, right, then normally what we would do is we would take theta hat is going to be x transpose x inverse x transpose y, right? And it turns out that this is going to converge, again, in probability to theta of f, right? And it doesn't matter what distribution we're working with there. And so, again, just to sort of reiterate what we're doing here with this non-parametric setting, we're thinking about, instead of making explicit assumptions about our underlying distribution, what we want to do instead is just assume that we have some distribution, something that we might not know a whole lot about, and then work from there to still be able to say things about estimates or estimators that are of interest to us. Okay. And the thing that I'll emphasize is that non-parametric statistics is a whole, broad field of statistics that you could study itself. You could take a whole course in it, probably multiple courses. So what we're going to touch on over the next couple of lectures is going to be sort of a very small segment of this, but we're going to see how can you start to form some non-parametric estimators. And then what we're trying to build to with this is how can we take Monte Carlo methods and actually use them sort of non-parametrically. And as soon as we're able to do that, what we're going to find is that we're going to be able to use this whole type of sort of non-parametric Monte Carlo to figure out the variance of just arbitrary estimators to allow us to do sort of all sorts of interesting things. We're going to be able to estimate the bias of an estimator. We're going to be able to do a whole lot. And sort of, the keyword that we're building up to here is to understand what's going on with the bootstrap, right? So that's what we're sort of working towards, the bootstrap, resampling, that kind of thing. So hopefully this made at least a little bit of sense. And again, if you have any questions at all about anything that was talked about in this lecture, please, again, feel free to reach out to me, set up a meeting, come chat. Otherwise, I hope to see you all sort of in person very soon.